Professor Reddy?
Sir. Sir, we'll start, sir. Participants will join.
Let others join. You want to introduce me or shall I start?
I will introduce, sir.
Okay.
Just for,
then you let me. Then I'll share my screen.
Okay, sir. I will stop sharing. Now you can share, sir. So, very good afternoon to all of you. I welcome you all to the second session of fifth day of faculty development program on Shalom D Foundations. So now we have with us the towering personality in geotechnical engineering, Professor M.R. Madhav, here to deliver a talk on static load tests on single pile and group of piles. So before Professor Madhav delivers his lecture, I'll present the biodata of him. Professor M.R. Madhav is an institute fellow of IIT Kanpur, and he is AICTE INAE Distinguished Visiting Professor. I am happy to say that very recently Professor Madhav is permitted to serve online university as AICTE INAE Distinguished Visiting Professor. So the students of online university now have access to Professor M.R. Madhav. So he is working as visiting professor at IIT Hyderabad and as a professor emeritus at JNTU Hyderabad. He is a research person at Rajiv Gandhi University of Knowledge Technology, and he is also serving as guest faculty at Engineering Staff College. He served as Chairman Research Council of CSIR CRRI and on Governing Council of JNTU University Kakinada. He is serving as advisor and consultant to various geotechnical engineering organizations, particularly dealing with geosynthetic applications such as Strata Geosystems, KSK, Halcro, and then Energy and Infotech, etc. He retired as a professor of civil engineering from IIT Kanpur. He is graduated in civil engineering from Andhra University in the year 1960. And I can say he is the distinguished and proud alumnus of Andhra University. He obtained his Master of Engineering and Doctor of Philosophy degrees from the Indian Institute of Science, Bangalore in the years 1961 and 67 respectively. Professor Madhav worked at several universities abroad. To name a few countries: Australia, Canada, Japan, Belgium, UK, etc. Professor Madhav's research interests span the whole gamut of geotechnical engineering. He guided more than 45 doctoral and several master's theses. He co-edited books entitled Lowlands Development and Management and Foundations and Soft-Ground Engineering Challenges in Mekong Delta. He has published more than 500 papers in referred international and national journals and proceedings of the conferences. Professor Madhav is a fellow of the Indian National Academy of Engineering, the Indian Geotechnical Society, the Institution of Engineers India, etc. He has won several prizes and he received many awards. To name a few, he was awarded with the Kuckelman Award of the IGS, Professor Mehra Research Award of University of Roorkee, Pandit Jawaharlal Nehru Bicentenary Research Award of CBIP, the Doctor of Science degree of ISC, the Bharat Ratna M. Vishwesvaraya Award from Institution of Engineers India, the Gopal Ranjan Research Award of IIT Roorkee, IGS MSJN Award, the Distinguished Teacher Award of IIT Kanpur, the Vishwakarma Award for Academic Excellence from CIDC, Professor Dinesh Mohan Award for Excellence in Geotechnical Practice, the IGS Emil Innovation in Design Award, the Outstanding Research Award from IAC MAG, the Distinguished Alumnus Award of the Indian Institute of Science Bangalore, etc. He was the president of IGS, and he served as vice president for Asia for the term 2005 to 9 of International Society for Soil Mechanics and Geotechnical Engineering, and served as president of International Association of Lowland Technology for the term 2008 to 10. He delivered a keynote lecture at the Asian Regional Conference at Singapore, the first Miura lecture in 2008, IGS Ferrocourt Executive Oration in 2010, and the first Victor de Mello Goa lecture in 2017, and delivered several keynote lectures. To mention a few, geotechnics of soft ground at Indian Geotechnical Conference 2017 at Guwahati, and he delivered first Professor Sriramarav lecture at Guntur and so on. He has delivered another important lecture for TC 207 of ISSMGE at Bangalore. He received the Reviewer of the Year award for the years 2016 and 17 from Springer and IGS. He is awarded with the Institute Fellow of Indian Institute of Technology, Kanpur in November 2019. Most recently, in March 2020, he was awarded the Outstanding Reviewer for the Journal of Journal of Geomechanics from American Society of Civil Engineers. Professor Madhav pursues origami as his hobby. So we are very fortunate to have such highly academic research and practice oriented personality in geotechnical engineering. He is known for his works world over, and I can say he is the topmost geotechnical expert, I can say, in the world. So all of you should feel proud to get a chance to listen to his lecture. You will gain a lot of knowledge. So I request all the participants to focus on whatever points Professor Madhav sir will deliberate during his presentation. With this, I request Professor M.R. Madhav sir to deliver his lecture on static load test on piles. Sir, your audio is muted, sir. Kindly unmute, sir. Arun, is it muted from your end? Arun?
Yes, sir.
Kindly unmute SARS.
Only Madhav sir can unmute himself, sir.
Not at the computer center.
Yes, sir.
Sir, kindly unmute, sir. Just Professor Madhav will be rejoining. he has some issue from his end.
Okay.
Now it is okay.
Right. Can you hear me now?
You are audible.
Okay. Very nice afternoon to all the participants. Very kind words from Professor Reddy. All I could achieve is because I had excellent students, not only Kanpur, from all over India and also a few from abroad, who made me what I am today. And I'm indebted to my students and co-workers who have contributed to my overall professional success. I would like to share with you something very interesting today. Pile load test, which is very different from plate load test in one respect. I, for one, would never recommend a plate load test because you cannot transfer the data you get from a plate load test to reality. For the simple reason, the plate size is very small, hardly 300 to 450 mm wide or diameter, whereas most of the footings we talk of are maybe 2, 4, 6 meters wide, and the zone of influence is much larger compared to the plate load test. And we should not do that too. If I can help, I would ban plate load test. Though some structural engineers insist they want something for the sake of the modulus of subgrade reaction. Unlike plate load tests, the pile load tests are absolutely essential. Why? Because when you do a pile design, you have some geotechnical data with you. Then we introduce the pile, and then based on the limited data we have, we try to imagine or visualize a pile of 600 mm diameter, maybe 14 meters, 16 meters long. The properties are very different at different depths. We may have different correlations and IS codes, but I can tell you, and you will see at the end of my presentation, none of them are exact or accurate. So when you do a design, you better check whether our design is safe, conservative, or unsafe. So we had to make sure, and the process of a pile itself could change the properties of the ground, and that may change the capacity too. So what I would like you to look at is that pile load test is not simply to get your allowable safe load. You can do a lot more diagnosis, and recently we have been able to even get the interaction parameters. So we'll try to cover as much as possible. I hope you would appreciate the kind of data that's being given here. So what I would like to cover would be what are the kind of types of tests we have, what are the procedures we adopt, how to, and I would say diagnosis is also very important. Load settlement data can tell you a lot more about how the pile is behaving. Then we have been fortunate to have some good students who have been doing analysis of the piles, and based on that, we are able to estimate the pile ground interaction. I want you to make a clear notice of what I'm saying. It is not pile soil, it's pile ground interaction. I, for one, believe there's a difference between ground and soil. Soil is an element which you can take it out of the ground and you test it in the laboratory. But soil or strata that exist in the ground is a very different entity. The behavior of the same in the field or in situ would be very different from what you find in the laboratory. Someday when I get a chance, or maybe at some later stage, if Professor Reddy can arrange, I'll show you that behavior in the lab is very different behavior of the same sample or same soil in the ground. So we'll try to cover these aspects in the next few seminars. When I look at the types of tests we have on a vertical pile, we can have axial compression, which is the most common one we have. We design our buildings to transfer the load through soft soil to hard strata, or even if it's intermediate, through shaft resistance. So most of the time, the load coming on the pile would be axial compression. But there are some situations where particular lateral load or some kind of moments coming onto it, some piles may be subjected to pull out, which means the axial load is acting against gravity and coming out of the ground. These are very few, but in a building or in a group, sometimes it can happen because of moment and rotation. Piles also take lateral load because, as I said, moment and wind load, or say the seismic loads. If you're designing offshore piles, you have wave action. If you're thinking in terms of bridge foundation, the water current, the traffic load, etc., may give you lateral load. So these are the ones that we talk of, and most of the time today closest to axial compression and a little bit of pull-out. We'll talk about lateral load maybe tomorrow. Then there are two types of tests one can do. It is called the initial load test, which you do before the construction of the project. This is what we do before we do the design and before we approve the final capacity. We need to test whether our design is correct or not. So it is called initial test. And this, suppose your allowable or safe load you designed for is about 80 to 90 tons, you have to go at least 2.5 to 3 times that. If you can go to failure, fine, but many times you cannot reach failure. So we say at least 2 to 3 times the design load you have to test it. Then on the working piles, we had yes.
Slides are not
visible.
They are not shared.
It was there. Now,
since you logged out and again logged in, so you have to share it again.
Yeah. Sorry. Now, can you?
No, sir.
No.
Sir, there under present now, the option is coming in other person.
Yeah, I did that. Okay. Again, I don't see that present now is, I've been doing it. Again, let me log out. Very strange. How about now?
Not yet comes.
No.
No, sir.
It's there on my screen, and I said share.
Share you select the share window and then choose PowerPoint. And
no, it's open.
so,
Present now, your entire screen. Okay. Then I click on this. Last time I did that. How about now?
now it is coming.
Okay, thanks. Okay, I'm sorry, I missed it.
Sir, you press on the hide thing. Right.
Now it's okay?
It's okay, sir.
Full screen.
You can make it full screen.
Yeah.
And to the right of stop sharing hide is there.
Yeah.
So, on that, sir.
Okay. My apologies for some technical problem. So the contents of my talk would be, I would like to talk about types of tests, procedures, interpretation, diagnosis, analysis, and pile ground interaction parameters. The types of tests we talk of, as I said, were mostly we do it for axial compression. We may like to do pull-out too, and lateral loads are the option we have where the buildings are tall or the tower is very high, particularly for all these wind turbines, etc. That is important. Then we do two types of tests. One is called the initial load test. This is done before the piles are installed for the structure's foundation. This is to verify whether our design is correct or not. If the estimated load is much less than what it is possible from the field, you can revise your design so that you save a lot in terms of number of piles. Whereas if your design load is more than the actual result from the load test, which means the soil is not able to take according to our estimate, so we had to redesign, maybe increase the number of piles. After that, once the construction starts, we have to test few number of piles, roughly 1 in 100, 1 in 50, 60. We verify whether the design load is being achieved or not, particularly with respect to settlement. Initial load test we carry on for 2.5 to 3 times the design load if failure is not possible within that range, and then we try to extrapolate to get the failure load. Whereas proof testing is generally carried out to 1.5 times the design load, and we make sure that the settlements are within the allowable range of, let's say, 10 or 12 millimeter at working load itself. These are the kind of tests we do. Then the kind of loading we can do would be, the types of loading is, you put a dead weight, it's called cantilage. So you have to create a huge dead load by, stacking one girders or concrete beams or sandbags, etc., so that you can take a reaction through the jack and get the loading. Other alternative would be, you try to take reaction from adjacent piles. Suppose I have a number of piles in a group and I want to test one of them, I can take reaction from the other piles and do it. Third would be, if I'm not having I can provide anchors, 2 or 4, whatever it is, connect them up and then take the load. In this case, the load is transferred back to the ground through anchors. It's very similar to reaction piles. Then in terms of the types of tests we do, one is called the slow test, wherein you apply the load in increments. And the increments according to our code is, of course, very, very unfortunately small number. They say 4 is enough. That means 25%, 50%, 75%, and of course 100% is. I, for one, would prefer a 10% increment in load, and then you maintain the load, slow maintain, so that the displacements more or less become constant under each load. Then increase the next load and go. That is called the slow maintained load test. Whereas some people, they want to get the undrained capacity, which means you do a quick load test, hardly you finish in 2 to 4 hours, and that is somehow will not give you the settlement in terms of the drain. Because whether we like it or not, when the load pile is applied load, it transfers to the soil, and if the soil is a saturated soil, there could be, particularly fine grain, there could be pore pressures. And if the pore pressure dissipates, we'll get some more additional settlement. So that's called the quick test, but then long-term settlements will be more than the quick test that you get here. The other one which people wanted to do, like your traction test, etc., it's a constant rate of penetration. Very common. It used to be that people were trying earlier. They push the pile continuously and take the reaction. That means the displacement rate is constant, but the loading rate is not. And if you can see the curves on the right, you can see here, the slow maintained load test gives you a lesser load than either of the two. Maybe at large displacements, they may all become equal, but at working load, you can see that the slow test is small. It gives you more settlements and less load. So we need to always go for a slow maintained load test. This is the type of loading I was mentioning to you. One is the first one you can see here. the dead load is here, and we take a reaction from there. We push it in. We have two reaction piles on either side, and then they're connected through a beam, and then we take the reaction from the jack here to load the central test pile. Similar to that, we have these anchors on either side. It could be ore, and the load is again transferred to the beam, and which transfers it to the, so the anchors will be, or like the reaction pile, they'll be under pull-out or tension, whereas the test pile will be under compression. And you need to take the displacement through a remote control, maybe a tortoise station or one of the latest equipment that we have. You can see the kind of load. This is a huge pile that they are testing. So the total load they were expecting was around 2,000 tons. That means the kind of cement block they put in, or maybe if you look at the person's height, it's maybe something like 8 to 10 meters high, which is a very risky thing. But this is the problem with most pile loads. If you want a high capacity and do the test, it can be very risky sometimes and very costly too. So please remember that pile load tests are very expensive, so we should be very careful and make sure that we can get away with minimum number of required tests for the initial load test. This is the typical Indian version where we keep on putting the sand filled bags, jute bags, or one of these polythene bags, etc. Unlike the blocks that we have. And of course, here you cannot get probably more than 200 to 300 tons capacity. And even to reach the top, you need to have some kind of a ladder or a slope kind of a thing. Then if you want to do the actual compression test, you need the jack, as you can see here. And this jack is adjusted so that you can get the reaction from the beam at the top. So please note that it's not a very simple thing we had to do one. But more recent ones are simpler than this. We'll see that way. When you want to measure the displacement, you have to have the support as far away from the pile here. So we put another huge, maybe beam or I section, support it far away, and put our dial gauge and take the displacement of the pile with respect to the datum that we have put in. So this is a dial gauge, but nowadays we have LVDTs and electronic ones too. So this is the kind of schematic we're talking of. We have the concrete blocks for reaction. On top of it, you have these girders. You have a beam, a set of beams here. Then on the cantilage blocks you put in here. And you can see the jack, the dial gauges. Usually it's better to have 2 to 3. One is not good enough because you have to have, if there is a slight tilt, you may have to find out how it is. And you don't know which side the tilt is. As it is, you can see in this direction, so they put 2, but you may have to put 3 to make sure that we get the total picture. And you can see the support system should be at least 3 times the diameter, but I would say you try to go even 1.5 times away from the pile center, because this loading is going to affect the response of the pile, as we will see a little later. So make sure that they do this. And one other thing I wanted to tell, but which maybe the industry some not like, make sure that the pile is not preloaded without your knowledge. This happened a couple of times in my experience. So what we do is we take the jack with us away so that the the pile contractor cannot preload. What if it preloads and unloads it? Next day when you go, what you get is only reload displacement and not the original one. This is another tested 600 mm diameter. And you can see very similar ones, a lot of sandbags, heavy I sections to do the whole thing. The load is sometimes not through a load cell. We have a proving ring also to take care of it. And here, as I said, you can have dial gauges or LVDTs. And this pit is to put the pile at the axial level and not at the ground level. Jacking method is another wherein, of course, this is the same thing basically. We are using hydraulic jack and then we keep pushing it, which is same as what we are talking about. In order to minimize the interference, what I keep saying, you keep it as far away as possible. In this case, of course, not cantilever, but more of anchors and reaction piles. And you can see that if this is the pile tested, the support system is very far. When you try to measure the load settlement response, if you have an idea of how it is going to be, I want you to visualize this. I want you to see this may be the total load settlement response, but if you look at the shaft response, the shaft is mobilized at a very small displacement. Let me assure you, most of the time, the shaft resistance is fully mobilized within about 5 to 6 millimeters of displacement. Whereas the base resistance takes a large displacement, maybe 10, 20, 50 mm too. So actually at working load, you can see the shaft is the one that contributes most of the load. So you should be able to see if you can modify your load test in order to find out. If you can't, we'll see at the end of my presentation how to estimate these thread components, how to estimate the shaft resistance, how it is mobilized and the ultimate value. Similarly, how the base initial stiffness and the ultimate base resistance too. This is what I call as you need to analyze the whole thing and not just say, I got some, safe load at 12 mm settlement. You need to understand how is this load getting mobilized in the pile. And sometimes you find that when you do the test in case of either dense or sands or medium dense sands or clay, you may get the shaft resistance, and then there may be some kind of softening possible because this is the strain softening you get after the peak. So you can see shaft resistance may not be fully mobilized after a certain displacement. So here again, I can show you the maximum shaft resistance is mobilized less than 2% of the pile head displacement. That means if I have, let's say 600 mm diameter, 10% is 60, 1% is 6. So within about 5 to 10 millimeters, you get the one. But further, there may be some softening and you may get less one too. Many times, what we do is we load, unload. So you can see here, if I have the time load curve, initially load is increased up to 300 tons. Then we unload. In the second cycle, the load is taken up to about 600 tons, unload, and then we go to the 800 one. So when I look at the displacements, you get the displacement, we maintain it, then we unload, we get some rebound, but then we go to the second cycle, the rebound is much less, so you have permanent settlement. And when you go to the third cycle and unload, you may end up with something like even 15 mm permanent settlement. This is particularly necessary when you have cyclic load coming onto or wind loads coming and giving you the kind. So this is the kind of curve you can get. So first cycle, unload, second cycle, unload, and third cycle. You can see, as I said, the permanent settlement is an order of 10 millimeters, total was 22. So the rebound is about, say, 50% or little less than that, and you get this kind of behavior when you do your stage loading or increments in cycles. I want you to analyze this kind of a thing. If it is possible, I want you to visualize how the load is being transferred from top to bottom. And I want you to visualize this something like your seepage. When you have seepage, the flow takes place from the upstream to downstream. And similarly, the load getting transferred from the top to the bottom. So as you increase the load, let's say here P, applied load is increased to, in terms of 1 meganewton to 2.5. You can see the base load is negligible at small initial load, and the base load gets mobilized only when you have a sufficiently large top load of, say, something like 6 meganewton, the base starts feeling, which means all the load is being transferred to through shaft. This is what I want you to realize. Somehow we think the end bearing piles are great. Only if you have extremely soft soil, it happens. In many of these soils of intermediate capacity or at working load, the base load is not very important. So I keep showing this in order to illustrate it is the shaft resistance which controls most of the time. Okay, then if you have the instrumentation, if I have only the top displacement gauge at the top, I can get the displacement at the top. But we have no idea about how much is the displacement at the toe. And the displacement, what you see is because of the compression of the pile and the settlement of the toe because of the soil is compressible. So these are the two things we need to measure. And in the modern version, you will find people are trying to measure the displacement all along the pile, which is a very good thing, and particularly at the toe too. So if you don't have an instrument, this is the kind of thing you get. But if you have good instruments, you'll be able to predict or measure the toe displacements are at an intermediate. I want you to realize the importance of interference. You know, even I do the Kentledge or dead weight, before I do the load test, this is the pile. I have the two footings here on which I'm putting, let's say, 600, 800 tons, which means that load is getting transferred through these two bases adjacent to the pile, and the soil below will try to get compressed, it will settle. So at its settling, it is trying to pull the pile down, so you will end up getting a down drag on the test shaft. Please remember, already the dead load before you started loading, the dead load itself is causing the pile some down drag. So if you don't keep these far away, these interferences will come in. So you can easily visualize the pressure bulb effect, and I suggest you keep this dead load support as far away as possible. We do the same thing during, if I load now, I find that the pile is trying to go down. It's, so which means the soil forcing, and on the test shaft, you get a different reaction here. So you do not get the ideal response that you expect. The load is getting transferred here, which means the loads is transferred to the pile and the support system is carrying less. So the soil moment here is negative, is upward, whereas here it is downward. It's a very complex interaction that you will find, and what we think is the ideal pile response, it's not really true. When you have reaction piles, what we do is one pile here and adjacent piles here, and we try to transfer the load here. These are the two reaction piles in a pile group. So when I connect with the beam and again take the load, apply the load, these are subjected to pull out here. Again, you have to maintain a minimum spacing of at least 2 meters away from the test pile. Otherwise, you may have get some interference. People say 2 meters or at least 3D, so which is 600 mm diameter means a 2 meters is good enough. So these are the kind of interference effects you will have on the pile. Okay, so you can see here the effect of these two would be loading and unloading, and when you unload, you will find the net settlement is much less than what you get during loading. This is what I wanted to show you with regard to anchor piles too. In this case, the load is transferred to the bottom of the anchor pile or the anchor. So these are the reaction piles, and zone of influence is maybe you can take some 1:2 kind of. So when the reaction is taking place, this part of the pile will get affected because of the load transfer on either side of it. These are the tension piles, as I said again. Influence zone, reaction frame, no forces. But now if you have, during loading, the tension pile may have some interference here, depending on the space. So if your spacing is more than 3, some codes specify 5, so you better decide that the spacing can be large enough. This is what happens. When I put the load, the soil will try to oppose, the shear stress is upward. But as far as the reaction pile is concerned, because it's being under tension, the soil is trying to oppose it, you'll have downward. In this close spacing, you will find that the two are interfering with each other, and the response of the pile may not be ideal, what you can see. There's another interesting somebody devised recently. He said, I don't want the whole pile to be tested. He wanted only a part of the soil bearing stratum wanted to get here. For example, this part is not necessary or required in terms of load transfer. So what he did was he cast a grout plug here, put a steel plate and pulled this up. So you have only the shaft resistance mobilized in the bearing stratum, and that is, we're not considering the resistance in the upper one. If you want to isolate, this is what is called the plug test. But again, I have one issue here. When you are pulling it up, here this is a load test, because it's pull-out test, we are getting the tension kind of a thing. The shaft resistance under pull-out may not be the same as in compression. That's another thing we will see. And sometimes you find that the plug movement may not be immediate, which means there's always a slack. You have to correct for it. And then if you correct, they can have an ideal. This is because it's purely a shaft resistance. You will find that the movement is, shaft load is mobilized at very small pile diameter ratios, maybe less than 2% as we expected. And after that, the shaft resistance be the ultimate value. This is called the plug test. The problem, as I said, when you have these heavy loads, and if you don't anchor them and make sure everything is perfect, this kind of failure. Let me tell you, it's not uncommon. Once we had, even with a plate load test in IIT Kanpur, we had a failure of the load because the way the load is distributed was not uniform, and the displacement is not perfectly horizontal. Sometimes it can tilt and give rise to all the problem. This is how a cantilever can fail. This is a pull-out test, which is very similar to load test, except the pile is being pulled up, so nothing very different. These are the D-test test. You can see the reinforcement is connected to this, and then jack pushes it up, and that's how we get the pull-out test. The displacement should always be far away, and you have to put the support as far away as possible to get your displacement safely. Don't let anybody get near the load. Make sure when you do the kind of thing. So this is the schematic of the pull-out test. This is the pile and goes into the jack, and then from the beam you take the reaction. And these piles will now be under compression because this is being pushed up. And so these are the two dial gauges. We have enough space so that the travel can be measured. Then when you do lateral load test, I want you to realize a very interesting aspect of it. A pile, if it is not embedded in a pile cap, it is free to displace and rotate at the top. Then it's called free head pile. Most of the piles we test in the initial load test are free head. But actually construct the real pile, it will be embedded inside a pile cap, which means it is not allowed to rotate. It can displace laterally. So the pile's head is fixed. Behavior of a free head pile is very different from behavior of a fixed head pile. So you have to use appropriate theoretical conversions or correlation so that whatever response you get from free head pile can be changed to fixed head pile. This is lateral load testing. You can have a pile and then get the reaction. What we sometimes do is use two piles and push each other. That's much simpler. Unlike in the case of axial load, you don't need a cantilever. Here you are taking reaction from another pile, but you are not measuring the displacement of that. But more commonly, here you can see here, taking reaction, you are displacing, pushing it one and measuring the displacement. But you can also have a two-way test, which means I have one pile here, another pile here. I put a jack and I can push both of them and I get buy one and get two kind of thing. So you're testing two piles at the same time and you can then get the response. This is much better way of doing it rather than taking reaction from a dead load or a pile cap somewhere, etc. So this will be a better way of doing the test. This is what I was telling you. I have a pile cap here and a pile, so I'm taking reaction from pile cap. This means only one pile state. If I have two piles, I can take reaction from each other and get the two-way loading. And this is the typical load, lateral load displacement. And I want you to realize that lateral load capacity is much less compared to the axial load. Axial load, we are talking in terms of say 80, 100, 200 tons of capacity, safe capacity. Whereas here you can see it's hardly 10 to 12. Why is that? You know, axial load behaves like a column, but in lateral load, the pile behaves like a beam. And a beam, displacements are very high. So even under a load of something like, let's say, 10 tons, the lateral displacement is about 2.5 to 3 millimeters, and we normally try to conduct up to about 5 millimeters only. Sometimes this could happen. When you're doing the test, there may be a separation between the pile and the soil if you're doing cyclic load test, particularly for lateral loads. You can see here, when you're applying load, let's say the pile moves to the right. When you remove the load, the pile can go back because it's more elastic. Soil being inelastic, it won't rebound. So which means there's going to be a gap. So when you're doing cyclic load, if you have getting cyclic loads on your pile, be careful if there is a possibility of separation between the pile and the soil. This is particularly true for offshore piles and all this modern wind turbine, ones where you have a very long pile and you may have large lateral displacement. The latest in this, which is probably the best thing that happened to our geotechnical engineering pile load test, is we have a load cell embedded at the somewhere in the pile. This case, it's at the bottom. This was originally designed or developed by Osterberg in USA. So it's called Osterberg or O-cell. So what we have is the load cell inside the or at the bottom of the pile, and you have the pump, and through a pipe I can inject pressure into the jar or load cell. So the bottom of the pile is loaded in compression. The upward one is being pushed up. So one load cell will give you compression at the lower end of the pile and a shaft resistance above. So you don't need any cartilage. All that you have is the reaction from the pile itself. And so this has become very common. And now they have been using it in a number of tests all over Bombay, I know Haryana, Himachal, etc. I believe the Bandra-Worli ceiling, the piles have been tested with O-cell, and you get the complete response because there's no need of the reaction at all. No cartilage, no reaction pile. The load comes from the soil, ground itself. This is the schematic. So when you apply the load here, this one is going down the bottom, so reaction is upward. The shaft is going up, the reaction from the soil is downward. So this is how the both shaft resistance and the base resistance are measured. But my only limitation is the shaft resistance you get under pull-out upward force is not the same as what you get from downward. There is one risk in terms of that, which we may have to analyze properly. And to overcome that, this is one of the nice alternatives. Don't put the O-cell at the bottom, but you put it at the intermediate of the pile length, maybe halfway, 2/3 from the top. So the lower part of the pile gets compression and positive friction, whereas the upper half gets the negative or pull-out test kind of thing. So you know the kind of shaft resistances, and recently one of my students has got the result and shows that the shaft resistance under above the O-cell, unit shaft resistance is very different from that in the below in shaft resistance too. Kind of mechanics of it. You have no imposed forces before loading. Once you apply the load, this load is downward. This load above the O-cell is upward. So please note that this is how the mechanism works too. And then the way the load is, again, I want you to realize in the O-cell test, the maximum load is at the bottom and by the top it gives a 0. But a traditional standard test or typical load test, we have the load is maximum at the top and it decreases to the bottom. So this makes a big difference in terms of uh, interpretation. But what they say is that the Osterberg said the load is going to the end bearing zone properly, whereas in the standard test, very little load goes. So if you have a bearing stratum, I would say go for O-cell test. Okay, so here are the different mechanisms I can see. As you keep increasing the load, what kind of mechanism that happens? This is end bearing, where you have all the load, mid shear, and then when you put the side shear getting into picture. So at various stages of testing, you'll realize that. And for this, you need different type of mechanism. So here, the reinforcement, and you need a displacement gauge if you can put it here. Otherwise, you'll only be getting the displacement at the top. Nowadays, people are able to put in some displacement transducers also. So I get displacement at the O cell itself. Load displacement of the upper part. This is one of the ideal ones. So this is a kind of expensive one, but better than your cantilever. Probably the O cell will cost you maybe about ₹1,00,000, but static load test will be much more expensive than that. This is the load displacement response of the top and bottom half, as you can see, and you can see the difference. Whereas in the bottom, the load may be the same, but displacements are very different. You can get some 20 mm as you go deeper because the shaft resistance is less and base load is more, whereas in the upper one, the shaft resistance is mobilized much faster and you get the maximum displacement of about 15 mm. And if you have strain gauges, this is what I would also say. I'll show you some more results of this kind later. You will find that measure, suppose I have strain gauges at different locations. I can measure the strain here, converting to load. I can see the load is transferred at different rates above and below. This is another way you can interpret the whole data, and that gives you a lot more information. Now, there are a lot of dynamic ones. One is called the small strain, which tells you the pile integrity, and then the large strain gives you the pile capacity. I think I'm not going to cover that because we have another lecture from one of our colleagues there. These are all small strain. You can tell what kind of defects are possible from the kind of response you get. It's called pile integrity testing. And you can find out the defect from the response, whether the bulge is there, necking, cracking, poor concrete. All of these are possible with the pile integrity low strain test. These are the kind of possibilities. Sometimes, this is a bigger problem. Most of the board piles, we had one case recently, the muck is not removed properly, so the pile didn't get any end bearing at all. Another interesting is the reinforcement is not vertical. And these are all, of course, the necking problem, bulging, etc. These are the kind of problems. This is the typical example. The concrete didn't go to the bottom, and so you have a gap here. And you can see bulging that happens in case of soil collapsing, and if this borehole is not supported, or what you can call, with either casing or a fluid. So basically, dynamic pile testing is preferable, but static capacity interpreted rather than measured from dynamic testing. We do not know what exactly it is. It's an analysis, but some people are very good at that. I again go back to our basic concept that resistance or friction pile, all the load is mobilized at small displacement, and whereas in the bearing pile, you need large displacement. typical axial compression load test. You can see you've gone up to about 170 tons, and then the displacement is around 12 millimeters. That's when we stop the test. This is the kind of load test you get. You may have to analyze it to how much of it is shaft and how much is the base. Failure load is tried to people estimate using different methods of finding out how much it is by finding out what is the increment in load for each millimeter or 2 millimeter settlement, and then finally you put in the asymptotic value, you get this value. Similarly, you have several methods. This is what extrapolation of our plate load test data, where you plot such load on log scale, find out the intersection of the two tangents. It's not necessarily ultimate load. I can say this gives you the yield load beyond which, if you increase the load, the displacements will increase much faster than the initial part. These are hyperbolic Shin's method, which is a very interesting one too. If you do not take the load to ultimate failure, he says, let's assume the load displacement is a hyperbola. So what he says is, let's plot settlement divided by load against settlement, and you will get a straight line, and the inverse of that gives me the ultimate load. The initial part gives me the soil stiffness. So this is a very common method of extrapolating the result. In this case, you are able to get near final load, but not the ultimate load. This is what you estimate. And you can see the criterion keeps changing. Davisson gives you a criterion saying that whatever is the load corresponding elastic compression plus the some constant based on the pile diameter, and you get this value. So one can work out different ways, and there's always a range in which you get your ultimate load too. So this is the Shin's method. You can see people have measured both side friction and end bearing. You can see that looking like hyperbola. So you're plotting the displacement by the, load by displacement, and you're plotting straight line. Inverse of that gives me the ultimate loads. These are different criteria that we have. I just put in. You can use any of these kind to estimate the ultimate load. Not ultimate load, but so-called yield load. So one of the most common things we talk of is 10% of the diameter of the pile is considered as a maximum. But as you can see in this case, the slope changes at some moment. So this is called the yield load, and this is the maximum load corresponding to 10% of the diameter. And so we can take this as our maximum load and use a factor of safety to get the working load. And you can also use some tangent intersection method. I fit in a tangent here, another tangent, but that's not a very reliable one. This is a Davisson method, who says you take an offset of 1/20th of pile diameter and then 1/5 of an inch, and that is what he calls as elastic line. He claims this as the failure ultimate load, based on which you can get back your safe load. This is the Shin's method, which I'm using quite a lot. You can see the load displacement is like a hyperbola. And so we plot here displacement by load against displacement, and I get number of points within a straight line, and the slope of that is inverse of ultimate load. So in this case, I can get 230, because maybe in this case, it's fairly close to the failure, so I'm able to get the ultimate load. Brink-Hansen uses some kind of extrapolation in terms of 50% of the ultimate load you get, and where you get 90% of the load. But when I look at a pile load test, I look at this kind of diagram. I can see in this case, you can see the capacity is almost constant after about, say, 2 to 3 millimeters. So I immediately judge that the tip is not taking any, and mostly the pile capacity is because of friction. In this case, I would say about 80 tons, 80 kg, this kind of thing, that load is taken by the shaft, and maybe another 10 kg by the base, etc. You can easily interpret. This is a typical ideal case where you have friction and end bearing come into picture. In a stiff clay, I can get strain softening as I mentioned earlier. In case of loose or soft clay or loose sand, I won't get this kind of softening. This is another, if there is a gap here, then I realize that there must be a slip, then the pile catches up and gets the second curve too. Okay, and in this case, it's a weak concrete, our pile shaft sheared completely, and so instead of getting this, I'm getting pile failure itself. Now this tells me the pile is taking load, but then the foil, there must be some failure below, and then you catch up with the rock again. In this case, the pile got initially displaced, some lift off, and then new bearing stratum has come into. So basically, when you're doing interpretation, please look at also these possibilities. Is there any chance of negative skin friction, either because of the loading itself or because of some softening or preloading that's going around, the soil may compress. What about groundwater conditions? So within the test, let's say the groundwater table is at a height of maybe 5 meters from ground level. But in the life of the structure, if the groundwater level rises, we'll have a slightly lesser load, so you have to take care of it. The most important thing for bridges is the scour. You're doing the test now at the bridge side from, let's say, from the top to the bottom. But if the scour happens, so you lose support in the top, scour depth or 1.5 depth. Okay. So if you want to take care of that, you have to provide a sleeve and measure the displacement only in that strata which you expect the support to come in. So basically here, you can see the sleeve is here. No load is transferred up to the bottom of the scour depth or where down drag is likely to be. In this case, soft clay. So if I'm expecting down drag, I'm expecting only resistance here. So I do not allow resistance to be mobilized over this too. Okay. So be careful about testing in these special cases. Pull-out test is much easier because it's only pure shaft load. So you apply the load in which is tension and you get the displacement and take a factor of safety. It's only no bearing at all, so you get only the shaft rest. This is the typical pull-out test, and I want you to look at the displacement. They're hardly less than 2 millimeters, and you get your total load maybe 60, 80 tons, which means I divide this load by pi dl, the cylindrical area, I get the unit shaft resistance. Load transfer, I think we talked a lot. This is again what I want you to realize. Load transfer is always interesting, how the load goes to the bottom. It's like a flow to me. So the base load is much smaller generally. Most of it goes to the shaft. So what people are nowadays doing into the steel cage, you try to introduce some reinforcement, strain gauges, so you can measure strains at different depths. You can put the load cell at different places. This one particular case study I have, wherein we have a pile, we have a load cell at the bottom and strain gauges, vibrating strain gauges at different levels. From this, you are able to get a lot more information as far as the pile is concerned, and you can see, I know the load mobilized at different depths over the length of the pile. So I have very interesting data. From here, we can do a lot of analysis. And I want you to see how the loads are transferred from the top to the bottom, different pile capacities. In one particular site, they have done about 8-9 piles. And here is very interesting. In this case, the load is get transferred up to, let's say, 300 newtons. Nothing goes to the base. Only once you cross that, the slip takes place possibly, and the load is going to the bottom. So these are the pile segments. Because I know the loads at different elevations, say, let's say the load is 60, and here is something like 10, 50 kilonewtons is transferred over 1 meter, from which I can calculate the shaft resistance. So I'm able to estimate the shaft resistance and over different segment. 0 to 1 meter is about 130 kPa. 1 to 2 is 50, 60. Like that, you can see how the whole thing is being transferred. And we're also able to measure the base load. So we have the base load response, the total response, from which I can get the shaft response too. So this is how you can improve your study by putting a load cell at the bottom, and you know the response of the pile in shaft resistance and base resistance. These are somewhat very interesting. And I want you to notice sometimes the pile base doesn't move till it gets some load. So that's something very interesting, because till that displacement, all the load is being transferred to the shaft. So the tip resistance is negligible. So these are the kind of test data that we had got from that particular case, where we had 400, 600 mm diameter pile, and we have the capacity of the piles. Pull-out test and do very similar analysis. This is the lateral load test data. And you're able to get about 12 mm settlement with about hardly 30 tons lateral load. This is a longer pile, but doesn't make a big difference. The total load is still 25, 24 tons. As I said, lateral load capacity is obtained only through beam action. So even if long pile, doesn't matter if the soil at the top is not strong enough, all the resistance you get is only from the top. It's a typical example of pure shaft resistance, no tip resistance at all. Then we realize that the pile is not clean. Even though it's 18 meters long and it ends up in a good stratum, the pity was the bottom obviously was not cleaned at all. So you can see about 110, 115 tons, or we get the load that is shaft resistance within 5 millimeters. This is what I meant in terms of your diagnosis. And you can see the contractor has done a good job in terms of pile testing. And you can sudden drop from here. Once you put the load, displacement increases by about 30 millimeters. It's a good one, wherein the load is both shaft and base resistance. Cyclic load test, good one. These are again pure shaft resistance, very little tip resistance here. And pile goes down once it crosses the 250 tons load, and the displacement is hardly about 10 millimeters. That's it. So this is a friction pile again, even though it's designed as a friction and end bearing tube. So this is the pity that unless you do the test analysis, don't ever take for granted that the end bearing is possible. This is a pretty good one in terms of almost linear up to 500 tons. There is some slight dip here, but then it catches up too. These are different load tests. So what we try to analyze would be, this is one of my students' work recently. He said, I try to look at the pile loaded. So this is a total pile, shaft resistance and bearing. So I try to put it as a non-linear Winkler springs. And so if I now put in the hyperbola for the total pile load, you have P ultimate and the pile stiffness. But I wanted to find out what is the shaft resistance. Again, I put in this kind of hyperbola here. K tau is the shaft stiffness, pile soil shaft stiffness, and tau max is the maximum shaft resistance. Similarly, the base is another nonlinear spring. So I have Kb is the subgrade reaction coefficient for the base, and this is the ultimate load, which means if I know the response overall, P ultimate and Kp, can I K tau and tau max, that is pile soil stiffness and the unit shaft resistance, and similarly base stiffness and base ultimate load. We could develop some simple theory to using this hyperbolic relation, and we could estimate now what are the different values and compare with what IS code is giving. I want you to see here. This is the average N value along the shaft 81, and if you correct for n using that formula, you get 44, and the tip is 151. But what I want you to do is, these are the estimated from the actual pile load test. I get 34 kPa as the unit shaft resistance from a pile load test. But look at our code, gives me 88 here. So the code is over predicting, whereas it is less. In this case, it's the other way. The code is predicting 58, whereas I'm getting 115, 56, 98. So many times the terms of the shaft resistance is all predicting, whereas the end bearing seems to be not too bad. But where do I get end bearing in many of the cases? So 16.9, 15.9 megapascal, which is very close. 8.2, 12.8. Again, code is predicting by about 1/3 or 50% of the estimated value. It is, code is under predicting here, but here again it's. So what I want to say is that by interpreting, I'm able to whether the code is reasonably good or we are over predicting or under predicting. This is the best part that you can do in your analysis. Okay. So what I would like to say is that pile load test is not just estimate ultimate load. You can use it to identify the defect. You can also find out the initial stiffness. You can diagnose the thing and define even the load transfer to suit your own condition. So I just would like to listen to you if you have any comments. I have a pun here. Parallel have so much in common. It's a shame that they will never meet. So if you like puns, it's a good one too. And I would like now to show you a very interesting picture, and I end up my presentation with my signature. Geotechnical engineering is a science, but it's practice and art. So I'd like to listen to your comments now. So I'd like if people have any comments, please feel free to talk.
I request the participants to raise the queries.
You can put in a chat box too.
Hello, sir.
Yeah, sure.
This is Kumar. Sir, I have a few doubt in that O-cell test.
Yeah.
As it was inbuilt in the reinforcement case only, after concreting, it was left like that or anything it was done?
No, actually it's not in the reinforcement. It is beyond that.
Okay.
The O-cell cannot be retrieved. You have to sacrifice it.
Okay.
It will, there's no way you can get it. But that's a good investment, maybe 10, 20, 30,000 rupees. But you don't need to put in all that heavy load to take reaction. That's why people go for that.
And in the play that whatever that load settlement curve which was shown and all, like most of the things, can you clearly explain that how to exactly predict that?
Basically, you have two components. One is above the load cell, another is below the load cell.
Yes.
If the load cell is at the bottom of the pile, whatever you get above the load cell is pure shaft resistance. So that load above that, load divided by the shaft area gives you the unit shaft resistance. And the load below divided by the pile cross section, you will get the base load at base load. And you know the displacement, so you can always use that to predict your under working loads. How much is the shaft resistance allowed? In general, I believe that if you have ultimate shaft resistance pi dl into tau, you need to take only a smaller factor of safety of 1.5, not 3, because whether you like it or not, all the shaft resistance will be mobilized. Whereas for base resistance, you need large displacement. So I use a factor of safety of around 3 to get my bottom out for the base. But I find in my experience, unless you have extremely soft soil, the base load is usually around 10 to 20%. Recently, we found another interesting case. There was a stiff layer in between, and if the pile is stopped at that place, we could get good base resistance also instead of going to below the stiff layer. It's a thin stiff layer. In thinness, it's a couple of meters, but below that. So the pile diameter is only about 400, 450, and about 4 or 5 times the pile diameter, the thickness of the layer. So we are able to take advantage of the stiff layer too. But load cell is a sacrificial one. You can't get it back. That's kind of investment you make to avoid dead load testing. Dynamic testing is very good, but the problem is you have to interpret. You're not measuring it. What you're measuring is on dynamic response, the wave propagation, and we have theories, but again, everything depends on how good is our input. Okay?
Okay, sir.
Okay.
Hello, sir.
Yeah, sure.
Yes, hello, sir. Good evening, sir. Sir, actually, it was mentioned that when we do the cyclic load test, between the pile and the soil, sometimes there can be some gap can be originated. So
that will be lateral load test.
Lateral load. Okay, sir. So if it happens, so what are the measures we can do, sir?
What you do is you got to realize the depth of the separation you neglected in terms of capacity. You have to estimate what is the depth over which the pile separate from the soil. So what I do is if I have cyclic load, I reduce the capacity from static load. Let's say the static load safe capacity for a pile is something like 10 or 15 tons. Under cyclic load, it may be only 2/3 of that because the separation will not give me the bearing on the top of the pile. So cyclic load is different from the static single load kind of. Clear?
Okay, sir. Yes, sir. Yeah, thank you, sir. So just one more doubt. Sir, in the just very last slide it was mentioned the calculation of IS code, and when we do the calculation on our own, when we correlate, sometimes the calculation can be vary. The values can be vary between these two. So when it varies, so which value we should consider, sir?
That's what I told you. Most people design based on IS code. But when I interpret the data, it doesn't follow. So I depend on the load test data and not the IS code. IS code is good for initial design. And honestly, IS code is still, I would say, very, very crude and conservative. Do a load test and try to use the data for redesign. The problem is people go for IS code and you sometimes find IS code is over-predicting and in few cases it's under-predicting. Now, if it is over-predicting, I'm in trouble. Under-predicting, I'm safe, but expensive. So what I say, this is how you do a load test and evaluate your design. And you modify the design. As I said recently, we had to do that because many times the site code cannot take care of all the possibilities. It gives some, if I have SPTN, I take 2 times the N value for shaft resistance and maybe 4 or say 10 times that of base resistance. It's a very crude estimate. They want to be very conservative and the consultant wants to be very, safe. He doesn't want to be sued because of using his judgment. So he designs according to the code. But if you are one at the side, do actual load test and say, is the code is safe or unsafe? And if it is over safe, how much can I go improve? Because let me tell you, the piling is a very expensive component of foundations. Probably, I believe, I could be wrong, but it costs around 8 to 10,000 rupees per meter length of pile for installation. So if I can even reduce the number of piles by even 10%, I save a lot of money for the project. And otherwise also it's possible that if you're under predicting, or predicting, you may end up having too much settlement. So always validate with your test. Okay?
Yes, sir. Yes, sir. Sir, in that, if we get the load value in the, let's say, if we get our value after the load test, if we are getting the lower value, but as per the IS standard, the value is higher. So we should consider the as load test, or we should follow the IS.
Load test. We have got less than the code, right?
Yes, yes.
Code is not a God, what should I say, sacred one. What you are tested is more reliable. Code is a guideline. Please remember, code is always a guideline. It helps you to start, but it doesn't predict how it is going to behave. So that way, it's, if you get slightly more, fine, but if you get less, you'll have trouble.
Okay, sir. Okay, sir. Thank you so much, sir.
Thank you. Okay. Thank you for everybody. Hope I'll see you again tomorrow morning.
Sir, thank you very much, sir, for covering all the details pertaining to static load testing of piles. So not only you have highlighted how to interpret the safe load and all. So the other things which the shape of load settlement curve explains, the philosophy behind getting a and all you have given. So this is what one should think instead of simply following the clauses of code and arriving at the safe load capacity. You should try to understand the behavior of the ground. And you have explained the participants about various methods of loading, conventional tented loading, reaction type loading, and latest ones, bidirectional load, wherein we don't require any templates and cost in carrying out load tests. So I hope all the participants have gained sufficiently good knowledge on load tests. So tomorrow afternoon session we will have load tests, dynamic pile load tests.
By Kiran, isn't it? That
By
Kiran Vaidya.
So that part will be covered tomorrow afternoon session. So thank you very much, sir, for giving such
Thank you. Have a nice evening. We'll meet tomorrow morning 9 o'clock.
Okay. And one more thing sir was mentioning is, whatever decision you are taking on safe load capacity of pile, the pile load test based value is the accurate one. Static analysis based values, even IS code to IRC method, many differences are there. So if you use one method, you will get one value. Either it will be overestimate or underestimate. Most of the times, particularly if you see IRC right code, the values will be much lower compared to the one which you will get from load test. So it is always advisable to check the safe load carrying capacity from load test and revise, instead of simply basing on static load test. Static analysis rules. So thank you very much, sir.
Thank you.
So tomorrow we'll have a lecture at 9 a.m. by Professor M.R. Madhav, sir.
Yeah.
The topic being lateral load capacity of single pile and pile groups. So most of you might not have studied about lateral load carrying capacity of pile groups, right? So that topic will be covered tomorrow morning. So I request all of you to join on time so that we can complete this session early so that your work is not affected. Thank you, sir, once again.
Thank you.
So thank
Have
you,
a
sir.
nice evening. Bye-bye.
I thank all the participants for attending today's sessions. So in case if you have any doubt on any of the topics that are covered, you are free to ask at the end of the sessions on any day. Okay. So as one of the participants is asking whether presentations can be shared. So if the speaker is willing to share PDF version of his PPT, we will be able to share it to you. Otherwise, whatever recordings that are there on YouTube you can have, or after conclusion of the course, we'll try to make lecture-wise videos and provide the links to have the access to video lectures. So that help we will do. So that's all for now. We'll meet tomorrow at 9 a.m. Thank you all. So before leaving, complete the attendance sheet that is shared in the chat box. Okay.